Hi and welcome. So in this video, we're going to talk through factored form of polynomial functions. So similar to quadratic functions, we can take a polynomial function and actually write it in factored form where we can see the horizontal intercepts. So I think the best way to show you this is just with some examples. So first, let's actually look at a quadratic, which is a type of polynomial, and see it in factored form. So here, let's say we have f of x equals x plus 4 times x minus 1. So this is factored form. We can see the horizontal intercepts from this, and this is still our polynomial. It's just written slightly differently. So we're going to go through our normal vocabulary. We'll talk about the degree, the leading coefficient, the horizontal intercepts, and the end behavior. So first, if we talk about the degree, this is a degree 2 polynomial. So the way we do this is by adding the exponents of each of the factors. So this is really like x plus 4 to the first power times x plus 1 to the first power. So we do 1 plus 1, which is 2. The reasoning here is that if you distributed everything properly, we would get the polynomial x squared plus 3x minus 4. And here we can more clearly see that the 2 is the degree. So we don't have to multiply this out every time. It especially gets complicated if the polynomial has a really high degree with lots of different terms. So instead, we just add the exponents on each of the terms. So here, the degree is 2, and we'll make a note that this is an even degree polynomial. Now, for the horizontal intercepts. The horizontal intercepts of a function are where the output is equal to 0. So I'm going to take my function and set it equal to 0. If a bunch of things multiplied together equal 0, one of them has to be 0. So we say either x plus 4 equals 0 or x minus 1 equals 0. Then from each of these, we get our horizontal intercepts. So I get x equals negative 4 and x equals 1. So this is exactly the same as we did it with quadratic functions. Now we're just using some additional vocabulary. So again, we'll do leading coefficient and then end behavior. Here I see the leading coefficient is 1, since there's a 1 on the outside, even if we don't write it. And this is a positive value, so we have a positive leading coefficient. And between an even degree and a positive leading coefficient, this means the end behavior will have both ends going up in the same way. So we have the left side going up and the right side going up. Now, what I like about factored form of a polynomial and going through the end behavior is it means we can sketch the general graph of the function, so we can just get a sense for how the function's behaving. Here I note the horizontal intercepts and the end behavior, which is enough for me to draw an OK graph. So if I have my axes, I know I need negative 4 and 1 as my horizontal intercepts, and then I know both of the ends go upward, so both the left-hand side and the right-hand side go to infinity. So from here, I know I have this parabola facing up that goes through these 2 points, and I can sketch my graph. Okay, so that is our first example, and hopefully illustrates to you why factored form is helpful. By knowing the horizontal intercepts, and then also being able to find the degree and the leading coefficient, I'm able to draw a sketch of the graph. So we need to introduce a little more vocabulary before we try this on another example. So we say the multiplicity of a horizontal intercept is how many times it appears in the function. So in our previous example, each horizontal intercept showed up once, but they can show up more than once, and I'll show you what that looks like. First though, when we're talking about the multiplicity, or how many times the intercept appears in the formula of the function, we divide this into being an even multiplicity or an odd multiplicity. And the idea here is that an even multiplicity intercept will behave like a polynomial with even degree. So near that intercept, it's going to behave like an even degree polynomial where both sides go up or both sides go down. So this means that at that horizontal intercept, the function will touch the axis and then bounce off. In the formula, this might look like having our factor to an even power. So we could have x minus 3 squared. That 2 is an even number. We could have x plus 4 to the 4th power, that 4 is an even number. We could just have x squared, that 2 is an even number. We could have x minus 7 to the 6th, that 6 is an even number. So these are all even multiplicity horizontal intercepts, and at that horizontal intercept, it's going to behave like an even degree polynomial where it just bounces off the axis and goes back up. Then odd multiplicity intercepts are going to behave like a polynomial with odd degree. So this is like our x or our x cubed. So at that horizontal intercept, it's going to cross the axis, and it might flatten out at that axis depending on what's going on. So these types of horizontal intercepts cross the horizontal axis rather than just touching it. So in the formula, this would look like x minus 3, that's to the 1 power, and what is an odd number, so odd multiplicity. It could look like x plus 4 to the 5th, where that 5 is an odd number. It could just be x, or it could be x minus 7 to the 3rd power, so that 3 is our odd number. So the multiplicity of the horizontal intercept depends on the exponent that goes with it. So we look at the exponent to see if it's even or odd. All right, let me show you this on an example. Let's suppose we have the function g of x equals negative 4x cubed minus 16x squared plus 12x plus 72. So this polynomial is written in standard form, and then we could write it in factored form as negative 4 times x minus 2 times x plus 3 squared. So if we were to take these terms and multiply them all out, we would get back to our original polynomial in standard form. So here we have one horizontal intercept to the power of 1, and our other term with the horizontal intercept to the power of 2. So we'll see how this changes the way the function behaves. So let's go through our normal things. We'll do the degree, the leading coefficient, and the end behavior, and then we'll also talk about the horizontal intercepts. So to find the degree, we can look originally at the standard form, so I'm seeing that the degree is 3, or we can add the exponents of the factored form. So that'd be a 1 plus 2, those are the exponents, which gives me 3 as the degree. So 3 is an odd number, so we have an odd degree polynomial. This means that one end is going to go up and the other end is going to go down for our end behavior. We'll just have to figure out which. Now the leading coefficient is going to be that negative 4. It's the number in front of all of those terms, or you can see it as the number in standard form in front of the x cubed. So negative 4 is my leading coefficient. That's a negative value, and so we have an odd degree polynomial with a negative leading coefficient. This means as we go to the right of the function, that end is going to be going down, so we have up on the left, down on the right. This information about the end behavior is going to help us sketch a graph. Okay, now let's talk about the horizontal intercepts just to give us a little more information. So the horizontal intercepts of a function are where the output is equal to 0. So where that y value or the output is 0. So we'll take our factored form, set it equal to 0. If these things multiplied together equal 0, one of them must have been 0 to begin with. So we can set x minus 2 equal to 0 or x plus 3 equal to 0. So we get x equals 2 and x equals negative 3 as our horizontal intercepts. Now we have a little additional work to do with the multiplicity, which is our new concept here. So on the x minus 2 term, the exponent was 1, so it only showed up one time. Since 1 is an odd number, this has odd multiplicity. So it's going to behave like an odd polynomial at this intercept. Then if we have x plus 3 squared, that has an exponent of 2. So since 2 is an even number, we'd say this horizontal intercept has even multiplicity. This means that at that intercept, x equals negative 3, it's going to bounce off of the point, like it's an even polynomial. So okay, we can piece this together one piece at a time. And we're going to use the information about the horizontal intercepts and the end behaviors to draw our graph. So I know I have horizontal intercepts at negative 3 and 2, and I know the end behavior means that we're going up toward the left and down toward the right. So I know where my ends of my function need to end up, and I know that we need to have intercepts somewhere in between. Now, this is where the multiplicity helps me out. So I know that the intercept of negative 3 has even multiplicity. So the function is going to come down and touch that point and then bounce back off. I also know that this is the first time it touches the horizontal axis. If it touched somewhere else, that would be another horizontal intercept, but we didn't get any other horizontal intercepts. We only got these two. So the function must come down, touch that point, and then bounce off. There are no other horizontal intercepts before this one. Then we also have a horizontal intercept at 2. So here this is an odd multiplicity intercept, meaning the function crosses through it. So the function must go up in some way, since it bounced up, and then it's going to go down through that intercept. And that helps us get the end behavior as we go to the right. So this is a super general sketch, but it gives us the basic idea about what the function looks like. So then when we go to graph this in Desmos, we're seeing it has the same shape, where at -3 it's bouncing off, and at 2 it's crossing through, and on the left side it goes up, and the right side it goes down. So these same principles can be applied to sketch a graph of any polynomial that's given in factored form. That's it for this one. Thanks so much for watching, and I will talk to you in the next one.